constructing exponential functions. Understanding discrete exponential functions. Recall that a discrete function has a graph consisting of isolated points. The table represents the cost of tickets at an annual event as a function of the number T tickets purchased. Complete the table by adding 10 to each successive cost. Plot each ordered pair from the table. So we're going to go 10, 20, 30, 40, 50, and that would be the point 330, 440, 550. Then we will graph those points. In B, the number of people attending an event doubles each year. The table represents the total attendance at each annual event as a function of the event number. Complete the table by multiplying each successive attendance by 2. Plot each ordered pair from the table. So 20 times 2 is 40. 40 times 2 is 80. 80 times 2 is 160. 160 times 2 is 320. And then plot them. So the function of t, the tickets, was linear. Is it discrete? Yes. Remember, we have two different things, discrete and continuous. G of n, is it linear? We're talking about this graph here. Would a straight line go through that? No, that is a curve. Is it discrete? Yes. What are the limitations on the domain of these functions and why? The domain is only made up of whole numbers. And the reason for that is because you can't buy half of a ticket, or you can't have a fraction of a person. Which is also why it's considered discrete. Continuous would be if you had fractions or decimal tickets or people. An exponential function is a function whose successive output, meaning the ones that follow, are related by a constant ratio. An exponential function can be represented by an equation in the form f of x equals a b to the power of x, where a, b, and x are all real numbers. A can't be 0, otherwise you would just have a straight line at 0. And b has to be greater than 0. You don't want any negatives. And you don't want b to equal 1. The constant ratio is the base b. When evaluating exponential functions, you will need to use the properties of exponents, including the 0 and negative exponents. Recall that for any non-zero number c, so if c or some number to the 0 power, that comes out to 1. If you have a number to a negative exponent, you can rewrite it as a fraction in the denominator and change the exponent to a positive. Complete the table for each function using the given domain. Then graph the function using the ordered pair from the table. F of x equals 3 times 1/2 to the power of x, with a domain of -1, 0, 1, 2, 3, and 4. The domain is what we plug in to the x values. So for f of -1, when we plug -1 in the x position, we get 3 times 1/2 to the negative first power. Up here, we saw that if you have a negative exponent, it goes into the bottom of the fraction. So in this case, the 1/2 went into the bottom of a fraction, which is essentially saying 1 divided by 1/2. If you use that leave, change, flip, that would give you 2, which is why we get this 3 times 2 here. So x is -1, f of x comes out to 6. So the point is 1, 6. Let's try 0. 3 times 1/2 to the 0 power. Remember, anything to the 0 power is 1, and 3 times 1 is 3. The first power. 1/2 to the first power is just 1/2. 3 times 1/2 is 1.5, or 1.5. 2. 1/2 to the second power turns out to be 1/4. 3 times 1/4 would be 3/4, or as a decimal, you could write it as 0.75. 3. 1/2 to the third power, that'd be 1/2 times 1/2 times 1/2 is 1/8. 3 times 1/8 you could write as 3/8. Or if you wanted that as a decimal, 0.375. Four, 1/2 to the fourth power would be 1/16. So you would get 3/16, or 0.1875. And now we graph. So -1, +6. Zero, 3. 1, 1.5. 2.75. 3.375. And 4.1875. B, f of x equals 3 times 4/3 to the x power. The domain that we're going to plug in is -2, -1, 0, 1, 2, and 3. In the first one, if you plug in -2, that turns into 4/3 on the bottom of the fraction. But then you could also think of it as flipped over, because you're dividing by a fraction, so you flip it over. So then the 3 would be on top and the 4 would be on bottom. Notice they still have those little squareds there. 3 squared is 9. 4 squared is 16. 3 times 9 is 27 over 16. 16 goes into 27 one time, with 11 left over. So 1 and 11/16. For -1, that's going to be 3 times 1 over 4/3 with a 1 exponent, but that just is, you don't even need to write it. It can be an invisible one, which then turns into 3 times 3/4. 3 times 3 is 9. 4 fits into 9 twice with 1 left over. Zero. 3 times 4/3 to the 0 power. Remember, anything to the 0 power is 1, and 3 times 1 is just 3. Three and 4/3 to the first power leaves it as it is. 3 times 4 is 12. 12 divided by 3 is 4. For 2, 3, 4/4 to the second power, that would be 16 over 9 times 3, which would be 48 over 9. 9 can fit in there 5 times. 9 times 5 is 45, leaving us with 3/9 left over, or you can reduce that to be 1/3. And now we graph. So -2, 1 and 11/16. It's a little bit over halfway. -1 is 2 and 1/4. 0, 3. 1, 4. 2, 5 and 1/3. 3, 7 and 1/9. What would happen to the function f of x equals ab to the x if a were 0? If a is 0, 0 times anything equals 0. So that would be a linear function. If b were 1, one to any power is always going to come out to 1. 1 squared, 1 times 1 is 1. 1 to the 15th power, 1 times 1 times 1 times 1, and so on, is just going to give you 1. So then that would be a times 1, and a times 1 would come out to a. So this is f of x would equal a constant. So this would be a straight line, a horizontal straight line at 0. And then this one would be a horizontal line at a. So if a was 5, it would be a horizontal line at 5. If a was -10, it would be a horizontal line at -10. Neither of those are considered exponential functions. They are both linear functions. Why is a geometric sequence a discrete exponential function? In a sequence, the values increase by 1, or the input values increase by 1, and the outputs are related by a ratio, like it explains at the top of page 665. It says that they come in the form f of x equals ab to the power of x, where a, b, and x are real numbers A can't be 0, B can't be 1, but the constant ratio is that base B. So it comes in the form of a constant ratio. Make a table for the function using the given domain, then graph the function using the ordered pairs from the table. If I plug in -3, that's going to flip that fraction over, and each of those pieces, the numerator and denominator, will be to the power of 3. Two cubed, that's 2 times 2 times 2 is 8. And 3 times 3 times 3 is 27. 4 times 8 is 32. 27 fits in there one time with 5 left over. And we can swap that out. Now we're going to plug in -2. So we flip that fraction over and it uses the +2 exponent. 2 squared is 4, 3 squared is 9, 4 times 4 is 16. 9 fits into 16 once with 7 left over. Then let's swap out that exponent with the -1. That flips it over, changes it to a positive exponent. That's just 2/3. 4 times 2 is 8. 3 fits into 8 twice with 2 left over. Now to the 0. Anything to the 0 is 1. 4 times 1 is just 4. Then we're going to put the exponent of 1 in. That leaves us with 3/2. 4 times 3 is 12. 12/2 is 6. Then we'll swap it out with a 2. That gives me 3 squared and 2 squared, which would be 9 and 4. 9 times 4 is 36 over 4 would be 9. And now we need to graph -3, 1, and 5/27. That's just a little bit over 1. -2, 1 and 7/9. That's close to 2. -1, 2 and 2/3. 0, 4. 1, 6. 2, 9. You can write an equation for an exponential function, f of x equals a times b to the power of x, by finding or calculating the values of a and b. The value of a is the value of the function when x is 0, because it makes that b equal to 1. The value of b is the common ratio of successive function values. So b is like that next output divided by the previous output. For discrete functions with integer or whole number domains, these will be successive values of the function. Write an equation for this function. When a piece of paper is folded in half, the total thickness doubles. Suppose an unfolded piece of paper is 0.1 millimeters thick. The total thickness, T of n, of the paper is an exponential function of the number of folds n. The value of A is the original thickness of the paper before any folds are made, or 0.1 millimeter. Because the thickness doubles with each fold, the value of B, that constant ratio, is the number 2. So they've written this equation. T of n, meaning the function of the number of folds, is equal to 0.1, that thickness originally, times 2 to the power of n. A savings account with an initial balance of $1,000 earns 1% interest per month. That means that the account balance grows by a factor of 1.01 each month. That would be 100% originally plus the 1% it grows each month is 101%, but written as a decimal, you move that 2 spots, so 1.01. That's where it comes from. And that is if each month no deposits or withdrawals are made. The account balance in dollars, so B stands for balance of T, which would be the time, is an exponential function of time in months after the initial deposit. Let B represent the balance in dollars as a function of time T in months. The value of A is the original balance, $1,000. The value of B is the factor by which the balance changes every month, 1.01. The equation for the function B of T is 1,000 times 1.01 to the power of T. Why is the exponential function in the paper folding example discrete? You can only have whole number folds. A piece of paper that is 0.2 millimeters thick is folded. Write an equation for the thickness T of the paper in millimeters as a function of the number of folds in. It started out at 0.2. It doubles in thickness each time. And you need the exponent. You can use given two successive values of a discrete exponential function to write an equation for the function. Write an equation for the function that includes the points. So because they are successive, meaning the inputs are the next one in the set, so 3 and then 4, find B by dividing the function value of the second pair by the function value of the first pair. So you're taking those outputs and dividing them. So 24 divided by 12 is 2. And then it says evaluate the function for x equals 3 and solve it for a. So what they're doing is they're taking that template and they found b already. So they're rewriting it. But then they have the points. So they're plugging in 3. But they know that it's supposed to come out to 12. So 2 to the third power is 8. And that can be rewritten as 8a equals 12. Then they divide both sides by 8, and they found that a is 3 over 2. Then they rewrote it as the function, filling in the a value they found and the b value that they found. Now it is our turn. So find b by dividing the function value of the second pair by the first. So 9/4 divided by 3. We can rewrite that as 9 over 4 times 1 over 3 if that's easier. 9 times 1 is 9. 4 times 3 is 12. And then we can reduce it. 3 goes into both of those. 3 goes into 9 3 times. 3 goes into 12 4 times. And it says write the general form. That's like the template. A, B to the X. We just found B, so we're going to replace that with the number we found for B. Since it's a fraction, it's best to use parentheses. Then it says substitute a pair of input-output values. So we get to decide which of those points you want to use. If it were me, I'm probably going to pick 1, 3 just because both of those are whole numbers. So 1 goes in the input and 3 goes in the output. Well, 3/4 to the first power is just 3/4. So now I have this. 3 equals 3/4 A. To solve for A, I need to divide both sides by 3/4. Or the other strategy you can use is multiply by the reciprocal, kind of like a fraction bust. But instead of just multiplying by 4, I'm going to multiply by 4/3 to eliminate that whole thing. 4 times 3 is 12. 4/3 times 3/4 is 1. And 12 over 3 is 4. So A is 4. And now we're going to go back to that original general form. And we're going to replace A with 4, B with 3/4. And then we have that exponent x. All right, so we're comparing. We are dividing the two values. 2 divided by 2/5. Leave, change, flip. That would be 5, because 2 times 5 is 10, divided by 2 is 5. That is the B value. So now I'm going to use this point just because, again, both of those are whole numbers. So I have f of x equals A, B is 5 to the x power. I'm replacing the f of x with the y value, which is 2. And I'm replacing x value with the x value, which was -1. So 5 to the negative first power turns into 1/5. Remember, we flip it over. Then we can multiply both sides by 5. 5 times 2 is 10. 5 times 1/5 is 1. So A equals 10. And then we finish it all off by rewriting it as A times B to the x power. Explain why the following statement is true. If B is between 0 and 1, and A is bigger than 1, the function f of x decreases as x increases. So what it's saying is, well, what if B was like a fraction? Let's just throw an example in there. If I had 1/2 to the first power, that would be 1/2. If I had 1/2 to the second power, that'd be 1/4. 1/2 to the third power would be 1/8. So why is it decreasing? And it says when you multiply by a fraction, repeatedly, the results decrease further. And this works for other fractions as well. You can think about 1/3 to the first power is 1/3. 1/3 to the second power is 1/9, and so it decreases even faster. Explain why the following statement is true for B is greater than 1 and A is greater than 0. The function increases as x increases. When you repeatedly multiply by a number bigger than 1, the product is greater and continues to increase further. What property do all pairs of adjacent points, meaning the points one right after the next, of a discrete exponential function share? They all have the same ratio. just like how we used to find b, where we divided to find the ratio. Any two successive points share those ratios.